after we write down the component, we consider the internal energy. The internal energy include by the temperature and also the kinematic energy, potential energy. So we can rewrite the energy equation become to this. Then for this term, basically we don't talk too much about the Fourier law. We will use the momentum equation for the component of this trace to discuss about this work part. And the last time we talked about how to determine this surface force in the momentum equation. I think last time we talked about the Stokes hypothesis. It's talked about this. And this surface force basically similar to this one, include the pressure and the shear stress. So if we rewrite the equation, like the momentum equation in 219. So continue we rewrite the different form of energy. So you will see the energy form basically they we represent by different form and different kind of assumption. Okay, so you have a different assumption. Your energy equation may be rewrite in the different form. So, for example, like this is the energy equation. Then we rewrite the internal energy related to the heat and the work. Right now, we want to specialize to focus on the work. So the work, this service force use our momentum equation we talk about in the Stokes hypothesis. Then we talk maybe spend a week to talk about this stress hypothesis. Then I said you can forget everything, but you must remember this. Okay, so the final result, because this also relates to the energy equation as well. So you can see the stress that relate to the pressure. This pressure is just like we mentioned in the Bernoulli equation. Pressure we correspond to the kinematic energy and the potential energy. Then they have a shear stress. This is usually the shear stress we are talking about. And the second shear stress, this part, usually we will neglect because in most of the cases, this term for the incompressible flow, that will become to a zero. But if the speed is very high and the flow is not, it's become to the compressible, this term, second viscosity will come out. Okay? So shear stress, to be clear definition, will be like the shear stress coefficient and the second shear stress coefficient. But this term, I think we also talked in the Stokes hypothesis. They have some relationship to this one, and in most of the cases we want to neglect this term. Then if we write down like the pressure and the shear stress, we write like this form. The work can be rewrite like this form by the viscosity and by the pressure. And by the pressure term, you can see this velocity because they correspond to the two directions. One is which surface, one is the velocity direction. These two directions must be the same for the pressure. Okay, so for the pressure curve, this, because we use the delta, this I and Z must be the same. So if we substitute the mass conservation equation to rewrite this term, to make this diverge, if we consider in a general case, then this diverge we can rewrite as invert over this, then by this term. This term will be like the total differential minus delta P. Because the pressure and the density, maybe both are change function. So if we make the Lagrange differential, we should make the pressure differential, density differential as well. That's total differential. So this term can rewrite like this two term result. So we substitute these two terms into this equation. Okay. So then we have one pressure and one shear stress. Then for this work term, from here, we can rewrite as this one. Pressure term, we will put in the same term with the internal energy, and left the dP here. So from here, we can see this is the enthalpy for the internal energy plus this pressure and density. And in your undergraduate, maybe it's internal energy, pressure, and specific value. Okay, this is set because density is an invert of a specific value. So this is the same. These two are the set. In most of thermodynamic book, maybe they will write down like the internal energy, pressure, and specific value. But this is same as this internal energy. Then you use the pressure over the density. Okay? Okay, so that's the left-hand side. We have our enthalpy. So enthalpy should change with the heat come into the system. We have a different kind of heat come into the system. And if you have a different kind of pressure, of course, increase the pressure, then we increase the enthalpy. This is taught in your undergraduate as well. Then I think this is a new thing for this one. The shear stress, this work, then we increase your enthalpy as well. Because this kind of friction force, then we create a heat. Then this heat will increase your system, this total enthalpy. Okay? Then we convert to the enthalpy or convert to the thermal energy. So for this term, usually it's mentioned as a dissipation function. Dissipation basically is reduce, quantity reduce, but basically they will reduce mechanical energy. But your energy equation should be conserved, but thermal energy will increase. So from here you can see thermal energy increase, but mechanical energy will reduce. So dissipation is mean mechanical energy reduced. Okay? So sometimes this function is mentioned as a Poisson function. Poisson is a scientist from French. Just like we mentioned before, Poisson tried to close the Navier-Stokes equation, but he didn't succeed. But people want to name after him to remember his contribution. In here, this kind of shear stress, they will induce some kind of thermal energy and reduce mechanical energy. This function is named as a Poisson. Okay, so sometimes this is a Poisson function. So for this dissipation function, basically we can write down like this. This must be positive because your viscosity, there's no way to reduce thermal energy. They only have a increase thermal energy. And your viscosity is no way to increase mechanical energy. Okay? So this must be positive for the thermal energy. So for this case, if they want to be positive, they have two conditions. One is your mu must be positive. And your lambda plus this mu, this relationship must be larger than 0. I think this you can do by yourself to check this function, how to become to the positive. They must have some kind of a condition. And this condition also Stokes give another hypothesis. Is these two relationships equivalent to 0? So use this relationship. You can define second viscosity their relationship. Second viscosity is become to 2/3 of a viscosity. Okay, so that's another Stokes hypothesis. Okay, so right now we talk about several different forms of energy equation. For example, from this energy equation, we can rewrite the energy equation into this term. So this we become to your internal energy and the pressure become to a left-hand side, become to an enthalpy. And the enthalpy we relate to the several terms. For example, like your pressure. Your pressure will change your enthalpy. And of course, your heat will change your enthalpy. And the dissipation by the viscosity will change the enthalpy. Also, from the definition of enthalpy for the incompressible flow, this is in chapter 1. Okay, so this is chapter 1 for definition of enthalpy. Basically, later on you can see the most of contribution for the enthalpy shown from which term. Anyone have an idea? First term. In your thermodynamics, they only consider similar like the internal energy. Okay, and this term for the compressible flow, especially for the gas, because of their pressure and their thermal expansion, we have some significant change. Consider the ideal gas. So compressible flow, we consider the later part. Okay? But for incompressible flow, usually this term is the most significant. After approximation, you will see the same result as well. Okay? But here we like to talk about complete and talk about assumption. Okay? So we take a break, then later we will finish this part.